Hello students, welcome back. Let's go to the next topic, expected value and standard deviation. We have section 3 and section 4, and I'm sure that I'll be able to cover section 3 all right, no problem, within week 4. And as for section 4, I'm not so sure. It may have to be carried over to the next lesson, or maybe we can cover it, I don't know. We'll try it anyway. Okay, here we go. Here is the definition of the expected value. Just multiply all the payoff value and then the associated probability value and then add them all up. The sigma notation here, Greek letter sigma, is actually summation notation, so add them all up. Okay, let's go to an example problem. Same example problem that we dealt with before. We have 5 red, 3 green, and 2 blue balls in an urn, total 10. And we have this game, game X. Alright, what is the expected value for this game? I have to multiply X and P, so payoff of $0 for red, and then probability for red, 5/10. And then $2 payoff times the probability for green, and $3 payoff times probability for blue, excuse me, and that's what we want. For red, for green, and for blue. It's just X1 P1, X2 P2, X3 P3, and then add them all up. That's the expected value. So this is 1.2. Okay, that's the expected value. Now, does it mean I'm gonna win $20 every time I play this game? Certainly not. This is statistics. Nothing is absolute. Nothing is accurate here. If you just keep playing, then on the average, I'm gonna win around $20 each time. Therefore, if I pay more than $20 each time I play this game in a county pair and do this many times, then I'm going to end up losing money little by little. Or more precisely speaking, there's more chance that I'm going to lose money that way. Now, if I pay less than $20 to play this game in a county fair, then as I repeat this game over and over again, I'll have more chance winning money little by little out of this game than losing. That's what the expected values are talking about. There's still uncertainty and there's still estimations. How about the next problem here? Let me copy and paste this thing and to change for Y. So same color distribution, 5, 3, 2, but different payoff values. And then this is just 50 cents, and this one is $1. So that is my expected value for game Y. Make sense? And this is negative 0.4. How about the third game here? Payoff is negative 1.25. And then what's the probability? There's no difference between red and green, so put them together. So there are 8 such balls. So this is a quantity we are looking for, right? So that's blue. And that's for blue. And this one is for either red or green. So let me use different color. And then let's finish this computation. What do you get in the end? My calculation yields negative 0.05. This kind of thing is expected value. Easy concept, easy computation. Now, what if you have probability mass function like this? Again, it's the same deal. This is a formula here. x1 times p1, x2 times p2, and so on. So just multiply these two. Multiply, 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 and then add them all up, and that is your expected value. Let me save time this time. So here's the color coding, and then here's the computation of the expected value. Multiply, 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 and then add them all up. Color codings help. Alright, does everybody feel comfortable with expected value computation? And then the theoretical meaning. Alright, one further comment about expected value. Many people call it probability mean and use Greek letter mu for expected value. In fact, when you specify the random variable, then we use this capital E of x most of the time. But if it is just a number after all those computation, for example, expected value of 1.2, in that case, we're going to use Greek letter mu more often. So this mu x expression is relatively, this expression here is not very common. Maybe. No, that's not really good either. So let me just remove that previous expression. Yeah, this is a little bit more common. So when you have calculated value, numerical value of the expected value, then typically we use Greek letter mu. Now, this mu is usually used for something else. The population mean most of the time. Population mean versus probability mean versus expected value. Are they all the same? The answer is, for discrete random variables here, in this case, they are the same, but not in general. Let me show you. So if your probability is just straight up counting and you have finite sample space so that you can count, then yeah, you can straight up counting. And then you can define probability through relative frequency. Number of outcomes in an event over the number of total outcome in the entire sample space, you see? So that's my probability. In that sense, you can write the expected value like this. x1 times p1, x2 times p2, and so on and so forth. And then p1 is relative frequency n1 over capital N. Capital N is total number of balls in that example we saw before, 10 balls. And then N1 was number of red balls, N2 was number of green balls, N3 was number of blue balls, remember? So we had those probabilities. Now, take the common denominator, and we have capital N, total number of balls, 10 balls, go downstairs, and then we have this x1 times n1, x2 times n2, and so on, and those can be separated like this, x1 plus x1 plus x1 like this. So in the previous example we just saw, 5 red balls, so the outcomes for red, the payoff value for red is added 5 times for each ball. And then for green, the payoff for green is added 3 times. So 1 for each ball. Same for blue, added twice, 1 for each ball. So what do you end up with? Basically, we just added up everything in the population and divided by the population size. We ended up with the population mean. So you see, in an urn and ball example that we saw before, there was a game, red then $0 and the green then $1 and blue $3. Was that it? Anyway, consider this situation. Instead of that, you just write those on the ball, and then 5 zeros, and then a $3, $2, and then $2, $3. Write those, and then consider that the population is actually a bunch of numbers, and then you can consider population mean like that. So what do we have? Population mean and the expected value actually mean the same thing in a special case when the probability is given by the relative frequency. By straight up counting number of outcomes in the event over the number of total number of outcomes in the entire sample space. If your probability is like that, then they're all the same. Of course, if you have infinite sample space and the probabilities are not just straight up counting, but some other kind of measurement, or even for finite sample space, if it is not counting some other kind of measurement, in that case, things will begin to break down. So in general, they are not exactly the same. So expected value and population mean are often equal. And at this level, at 3000 level, they are equal for every finite probability distribution problem, but not in general, to tell the truth. So expected value is a little bit more theoretical term. Probability mean actually mean the same thing as expected value. Population mean, as a matter of fact, is a special case. And most of the time they're the same, but beware. Okay, so much for additional comments, and let's go to the next topic, variance and standard deviation. And here's the definition. Remember, mu is the expected value. So x1 minus mu, what is that? That's the difference between the payoff and the expected value. Now, we squared it, so I made everything positive. Without the squaring, if you just calculate this, then you're going to get 0 because pluses and minuses will cancel each other out. Because I squared everything, I'm measuring how far away each payoff value is from the expected value. And then I multiply the probability and then add it up. So basically I'm taking the average. So on the average, how far those are. So how spread out those data are. Did I say data? Excuse me. That's for sample variance. This is population variance, or excuse me, probability variance. So it's more theoretical. So the payoff values of theoretical values are more dispersed for big variance. And then of course, vice versa, more concentrated toward the expected value, then I'm going to get small variance. Same for standard deviation. It's just square root of the variance. So big standard deviation means more spread out, big spread, more dispersion, and small standard deviation means more concentration. Well, so much for theory, and let's do some computation, and it's not too bad. It's rather easy actually. Let's calculate the variance here. So the probabilities are 0.5, 0.3, 0.2 respectively. Those are the same. And here I want x1 minus mu squared, x2 minus mu squared. Remember, mu is the expected value. x3 minus mu squared. And that's it. So I ended up with 1.56. Alright, it's not too bad a computation, even though it can be a pain in the rear end if you have really large numbers. Up to 3 numbers or 4 numbers, yes, you can do it with handheld calculator, but if I give you something like 7 numbers, then you can't, it's too complicated. Okay, the probability standard deviation is Oops. Like this. How about the next problem? Again, it's the same deal. You see? Deviation squared, deviation squared, deviation squared with appropriate probabilities, add them all up. So what is the variance of y? So we have to calculate that, right? Let's see, remember, we need squares here, squares here, squares here. Probability is always set, but here I have to subtract the mu value. Subtract negative 0.40, so it is plus 0.40. And then all I have to do is to calculate this expression, 1.24. Don't pay too much attention to how to calculate part. Oops, what did I click? Sorry about that. So square root of 1.24, yeah, okay. That is my probability standard deviation. So that is probability square root of 1.24. And that is approximately like that. Okay, all right. Okay, so we went through some computation of variance and standard deviation. Now, what if we have probability mass function instead of that earned model? Well, like this. And then we can calculate the expected value rather easily. Just multiply, 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 and then add them all up. And there's a computation. And as for variance, each payoff value, 0.50 minus mu value 1.5, square it, and then probability. That's going to be this blue. And then repeat that for red, green, and brown. Add them all up. That's my variance. And then take the square root, and that's my standard deviation. It's just a computational formula, so no big deal there. Now, what if you have a cumulative distribution function instead of the probability mass function? This may be a bit more complicated, not because the computational method for expected value, variance, and standard deviation are harder, but because there's an extra step from CDF to PMF. Once you get your PMF, you can do exactly the same thing as you did before in part A of the problem. So here's a review. This is CDF, which is obtained by cumulative, so by repeated addition. In order to go backward, you have to subtract to get the probability masses. Remember? And then once you get that, we get this probability mass function. And from here, you can easily calculate the expected value, variance, and standard deviation. The other computations, I'm going to leave the details to you. Yeah, nothing fancy here, just apply the formulas. The hard part usually is getting PMF from CDF, and here's the deal. We have to do appropriate subtractions for that. We discussed it before in the previous section, and I'll refer to it if you have any further question about that. Otherwise, that's it. We are done with section 3. Thank you.